prediction based on all-sky image. This is the outline of today's presentation. First, I will give a brief introduction about research background and motivation. Second, we will move on to our dataset and how we predict solar radiance. Finally, we can see the performance of the proposed machine by several revolution index. Solar energy cannot provide a stable power supply due to its intermittency. In addition to the solar photovoltaic conversion efficiency and the local global irradiance, the amount of the solar power generation is still affected by the solar zinc angle, sun occlusion, module temperature, light loss, and the module annual delay rate. Apart from the cloud occlusion has the greatest influence on the predict of solar radiance. The system is established to predict the cloud movement by image processing to improve the predict of solar radiance. This is the structure of solar radiance estimation. There are three inputs, as the diagram shows. First, the global weight are the image about cloud radius and the cloud thickness. Next, regional weight are obtained after performing the cloud filter extraction. Finally, consider the time vector. The long short-term memory, LSD and long short-term memory is used as a training model with cloud weight as input for the solar radiance estimation. In this article, I will show the structure of solar radiance prediction. Different to estimation, we're using optical flow to calculate the average moving vector between the last frame and the least frame. Then use moving vector produce the predict image. Then extraction regional future weight from this predict image. Consider the estimation solar radiance as the input. Use SLTN to train model and predict solar radiance. First, this image is open dataset from measurement and instrumentation data center in America, Colorado. It provides all sky image every 10 minutes. Second, we pre-processing image and the crop image in sun area. Then I will introduce how we extract the sun area and the cloud filter. To crop the sun block image from the all sky image, the coordinate of the sun on image need to be found. The position of sun can be described by sun zinc angle and the sun azimuth angle, but in real world, the curvature of the lens must be considered, and through the deep neural network to fit in the curve of observer coordinate. Moonlight is sun location, bicacular solar zinc angle and the solar azimuth angle. Red dot is sun real position, and the black line showed after deep neural network training result. So we can extract sun position in image real position. RP machine. This machine is a way to identify cloud. Its advantage sky and cloud can be well classified, but its disadvantage is thickness of the cloud cannot be presented. So we propose improve RP machine to solve this problem. Dividing RP by Y value. Y is image brightness value. We estimate sun area to 0 when Y over 0.9, like figure RPSV. Blue area represent sun area, and the RPSV value segment to 16 value as regional cloud filter input. In this article, I will introduce the optical flow. Optical flow is a way to estimate object motion through the optical flow machine. The motion of the cloud from last frame to current frame as the average moving vector. Lucas Canade optical flow through this square machine to get approximations of U and V. Let's show an example of the optical flow between the two OSI image obtained by using the optical flow machine. This T-1 image and this T image. Yellow array are optical flow vector. Assuming that the speed of the cloud remains constant, and make the predict image at T+1 by using the back projection machine. Then extraction regional future wave from this predict image. This is my LSTM model set up. Our data set have 3 months from 2018 January to 2018 March. 80% data set for training, 20% for test. Here, 3 performance indices are accurate to evaluate the performance of the prediction in the study. The stable is the best training output of the solar irradiance prediction. This is one training result. Blue line is real solar irradiance. Orange line is predict result. These are MAE about predict 10 million, 20 million, the 30 million, 20 times result. These are MSE 20 times result, and the R square 20 times result. Then this is my future work. My future work one is to improve the accuracy of cloud movement predicted by CNN optical flow, and add more conditions like temperature, UV, wind speed, or wind direction will be considered to predict better. Thank you for your attention.
Open the floor to the questions. Do we have the questions? So, if no question, I have a question for you. First of all, would you please, so for the one who come on stage to present your work, please bear in mind. Oh, yeah, I found your page number there. I don't know why. Find the page number. Okay. Then no issue for the first question. Then the second one is about the data allocation. So I do remember you use 80% for training, right? And then 20% for testing. Yeah. So may I know why? And then you pick up the RMSE or some other measurement to the RMSE and MAE as a key index to measure the performance. And I know the reason why did you choose these two. Is there any other research group conducting a similar research? Yeah. And if the answer is positive, can we have some comparison? Sorry. Okay. First one, the reason. Okay, you have the data allocation. Then 80% for training, 20% for testing. May I know why? Why did you choose such kind of arrangement? Most of the time they use 70% or 30%, and then you use 80%, 20%. Right? May I know why? And the second one, you choose the MAE, RMSE as a key index to measure the performance. So again, I want to know the reason. Yeah. And is there any other research group conducting a similar research? So if they use the same index, then it should be fine to me. But if the answer is not, then I want to know the reason.
First, training choose 80%. Just all people use 70 to 80. I feel it's normal, so I use 80. I think many people use 70 or 80 or all use. MAE and RMSE choose these performance index. MAE can check your average error. RMSE can catch if any error, any peak. IMAC can show more picker problem. If our average error have many picker, its IMAC will very high. So Iranians need to check have your accuracy more high or in anti IMAC can check his vibration status. If more high or too high, too low, more picker or many picker, it can catch how many, it can catch pick problem.
So is there any other research group conducting a similar research?有别的research group 做类似的研究吗？ Okay, so they also use the IMAE and the IMSE.
Yes.
Okay. Then why did you put the, okay, sorry, can you please next time you put the comparison table? Since we have the computer right, and then they're doing a similar research, so I'm pretty sure they have some result. So then if you can give us the comparison table, then I know how good the proposed algorithm. Yeah. Thank you. So who will be the next one?
And hello everyone, welcome to my presentation. I'm a reporter, my name is Benjamin. My advisor is Professor Lee. The target of my research is design and simulation high-PID control on a copter. Sorry. And this is my outline. First, I will introduce mathematical model and say about several control methods and show my simulation. And the flight of drone has always been a matter of concern. UAV are divided into multi-axis flight, helicopter, and fixed-wing aircraft, each with its own advantage and disadvantage. The advantage of a copter is that it is easy to control and simple to adjust the meter for experience. So in this case, we will focus on copter control and simulation. Noted, there are various control methods to control the flight of copter, such as PID, adaptive fuzzy control. This is the IPID control based on PID and derived from model free control. Compared with the traditional PID, this control has more estimation of the model, and it is used to control the error between the measurement value and the ideal value returned by the sensor or the sensor. And this is mathematical model. There are two types of mathematical model for copter. One for plus type model and one for X model type. The plus model is better for analysis, but the X model is better for actual flight control. So the X model is used as a control model. And the following is a mathematical representation for the 4 axis vector, which include the position state x, y, z, and the altitude state rho, h, yo. And the altitude is the angle of rotation of the object around the coordinate system. And where is U is control signal, G is gravity parameter, I is moment of inertia for x, y, z axis, M is total weight of protractor. And gate control. Gate control, proportional integral derivative control is very widely used and has the advantage that the control doesn't need to know the system model in advance and only need to exploit the error between the initial value and the ideal value. The following is a mathematical equation. And we have incremental PID control. Because continuous mathematical equations are not easy to execute on program, incremental PID was developed as a form of representation for PID digital control. The following is a derivation of the formula, where k is the number of samples taken. Unlike the continuous PID, which varies according to the processing speed. And model-free control. And model-free control is based on a mathematical control and combined with online number equation. IPID control is corrected by its input signal to eliminate the unknown parts and combined with the general PID control method to get a better control effect. Take the raw angle as an example, because we know the coordinate model. We can use the both equation with incremental PID to write the actual equation that will be executed. And here use magnetic simulation, and you can see the red line is no traditional PID control, and the blue line is IPID control, and zero line is reference signal. And this is 3 altitude angle result. And in this case, use MCU with sensor to achieve the control of the aircraft. The following is the hardware structure about the library. MCTN, Macro Control Timer, is used to control the electric governor, which can control the brushless DC motor. UART is used to receive and transmit the altitude sensor, and SCTN is used to receive and transmit the altitude sensor. And And we use the HC06 and communicate with cell phone in order to send comment or receive data. And the utilization of the hardware still need to adjust. So it is still a lack of extra bit. And in this case, the mathematical model of quadcopter was introduced and then simulated using IDID control. And the actual quadcopter was used to do the flight in order to achieve better result. And this is reference and the image source. And thank you. Thank you.
Is there any question from the floor?
Excuse me. According to your video, there should be an between the presentation. It is necessary to present the simulation site.
Because the aircraft is currently on top of the test flight platform. It's focused on did you go first? Okay, that's it.
May I ask for your research topic?
Okay. Please.
Have you using this model in real life on this quadcopter? Do you have any experiment video that can show us your experiment?
I have a video by this. No, I have a good resource, and I'm not taking on the DVD.
Then can it fly?
Can I fly? Yes.
Can it fly by your PID?
IPAD control, yes.
Okay. Yeah, I have no more question now.
Thank you.
Would you please navigate the slides to page number 11?
Okay.
Yeah, this one.
Yeah.
So I found that you use the Bluetooth as a main protocol to control your aircraft flight.
Signal, yes.
So you use Bluetooth.
Bluetooth for mobile phone to comment.
Yeah. You use mobile phone and then through the Bluetooth protocol to instruct your aircraft flight.
Yeah.
So may I know what is a target application field? Yeah, because Bluetooth it does have the range, right? It's a range about like if I'm mistaken about 15 meters.
First I use Wi-Fi for the communication, but Wi-Fi is not very point to point. Yes, so I use Bluetooth to receive and transmit some comment or data.
So you are using questions? And if no question, we welcome the next presenter.
Okay. Good morning, Professor and students. I am Tim Wei Liao. I am pleased to be here to share this research with you. The topic of the autonomic plan training algorithm, a plan to mobile platform. This is today's outline of presentation. First, I will give a brief introduction about research motivation. Then we will move on our next plan training start. Body control, PIDN controller. Next, we can see the generation of the name. In the end is conversion and reference. In response to Industry 4.0, the automatic and the intelligence of vehicle can be improved. If a device can return shooting and use the unmanned vehicle to replace the manpower to reduce the cost of transportation. This use the plan training combined with the QR code presentation to reach the topic, and use the body control system to achieve the obstacle event function. Body systems conversion and updates the control value of the all-wheel drive vehicle in real time. This is my hardware structure of mobile platform. The main control board is used 32 on. There are three types of sensors in the input, which are the whole sensor to feedback the correct stand by tracking and actual interval. Accessory sensor to discern motion length. Gyroscope sensor detect the angle, and the other send at motor drive mobile platform and the robot arm. The control is real-time through the GPIO and the timer. In the MCU, the image is recognized and converted by the third-party bit and set back the MCU through the UI. That reduces the mobile robot of SafeMate. Main controllable is ESK32. The third party with two webcams to recognize QR code. The QR code is detected on ground to get the correct location, and the other is detected in front of the robot to get a package information. And use the 12 voltage battery. The power board is 12 to 5 DC converter. The robot uses the stand motor to control filter and the vehicle movement. Movement is two-wheel drive use a DC motor. Gyroscope sensor detects the young angle. Ultrasonic sensor sit on the left, right, and the front. The whole sensor feedback the RPM. This is a system portrait of my experiment. First, read the QR code of the target point. The plan of the pins. Use the camera to read the position of the mobile platform and use move forward. Use the PIDN controller to achieve a speed movement. Work if the QR code is displayed. Determine whether it is target point. If so, stop all movement again. And if not, determine whether there are other drugs like the turn left or right until the target point is researched. The plan is made to along the target object to find the cross spring and reset plan from the start point to end point within a different arm. When planning a scan plan, the following need to be considered. Need to know the start point and end point, location of the obstacle, search next. This is the algorithm compare table to compare the best search extra algorithm and the A-star algorithm. Extension speed dash search faster than A-star. Number of the search you can see the figure 5 is the loss is the A-star. In the big 6, the ground score is N, not N. In the red star is the endpoint. In the orange is obstacle. In the distance use 5 pixels. And this is the A-star state. The node will the smaller cost as the next start point. When you reach the next start point, see the first start point and the node not solution to be as the obstacle. The best and finally can be found. It's a simulation. The red line is the best plan found at the end of the A-star algorithm. In this video, we use the 3 ultrasonic sensor and the gyroscope sensor as the input for body control and see the touch RPM. Propose to keep the movement in a certain to stop when there is obstacle in front of it. Here are the input communication of the body system. This is raw. When the distance is within 13 cm, make the mobile platform stop and return the basic command. When ultrasonic right is determined as near to make the lift turn. And when the ultrasonic sensor lift is detected as near to make the show right turn. And stick at the concrete stick at the judgment of drawing goal to keep the mobile platform in the center. This is a simulation of body control. And the development and the mobile platform coordinator. This picture is to show the right of step 40-degree display of each parameter. In this display also show the 40-degree shift of the left and the right both of which are convergence. In the takeover the introduction of the PIDNN controller, the controller stand control usage. You can see a structure arrow equal R in temperature minus correct body. X1, 2, 3 are the key proportional I integrate and the D derivative. K is differential coordination, U is controller, N is mobile platform. The simple neural PID controller uses the shown in the figure. The mathematical formula of the PID weight is following. Eta is the learning rate of the PID. The controller output of PID is as follows. K is the proportional correlation. The larger of K, the faster will respond state, but is more stable. The finding is step weight is used as the implementation factor of the calculation. As the movement finish the constant state control. This research has completed at the Arduino planning based on the QR code fixation, combined with the body inference and the PIDN controller, which is literally a plan to be optical advanced controller of a gradient vehicle. This is my regards. Thank you for your attention.
So, any question from the floor? Excuse me, can you go back to page 21? Okay.
why you use VIDEO0034 and what is the difference to VID? Okay. In traditional VID controller need to use very more time to do the experiment. You need to try and able to find the best KDK ability. And then the VID00 can learn by itself. So I use the VID00 to train the KDK results. PID is offline or online? And if it is offline, why you use online? Okay, it's offline because this is for the application. You need a short time. And the PID, you can see the bigger this page. The bigger turning the weight needs more time, about 13 seconds to convergence. So using the application is not good. So I trust the offline. That's all.
I just want to ask a question that out of this topic. Would you please turn to page 6?
Okay.
Where did you find this model picture?
It's true. It's by myself.
May I ask,
Uh,
how did you make it?
How did you?
It's too beautiful, I think.
Okay.
Just-
This robot is made for the contact and view competition, which is made to face the application. It's the religion application for the contact and view.
If you don't mind, I would like to ask you after this course. Can I?
Yeah. Okay.
Okay. Thank you.
Thank you.
So, can we have the next presenter? Next one.
Hello everyone, my name is Paul Ying Huang, and my advisor is Professor Chen Hongli. Today, I'm glad to have a chance to present my research. The topic is Object Data Analysis with Transformer-Based Object Relation Finder. And this is my outline of my presentation today. First, I will introduce the background and related work of my research. Second, I will talk about our method and architecture. Then I will show the experience result and demo the video. Finally, I will conclude today's presentation. And let's begin with introduction. A basketball analysis system is an essential tool in modern basketball game. And one of the important tasks is to find the ball handler. In basketball games, because of the complex overlapping events between players, it is easy to commit error when judging the ball handler, which poses great challenge to the task of judging who is holding the ball. Also, there are few proposed solutions for this task currently. So we found that if we use traditional operation such as IOU or calculating the coordinate distance between the player and the ball, it will lead to a serious misjudgment of ball handler. Or we need to collect a large amount of image data for CNN to learn. Therefore, we propose object data analysis with transformer-based object relation finder to solve this problem. And in this picture, we can see the player is always overlapping in the games, which makes it difficult and challenging to judge who is holding the ball. The main contribution of our research are following two parts. First, we create a basketball training data set. The label content of this data set includes bounding box position, width and height, object class, shaping ID, and ball handler. Through the framework we propose, we still perfectly judge which player is holding the ball when complex overlay of player happen. In the end, our ball holding accuracy is better than traditional aberration and image classification based on reasoning. And let's talk about relative work. IOU is a method to calculate the overlap of the bounding box. We calculate the overlap between the box of the ball and each player, and take the maximum IOU value to determine which player is holding the ball. And the following is the calculation formula of IOU. And Euclidean distance is used to calculate the real distance between 2 points in space. We calculate the distance with the ball and player, then take the minimum distance value to determine which player is holding the ball. And following is the Euclidean distance formula. And ResNet is one of most representative network architecture of CNN. ResNet proposes a network for residual learning, which can reduce the error rates while deeper more layers. We use our own basketball dataset from ResNet to image classification, hope to predict which player is holding the ball. So we train 3 different architectures for experiment: ResNet 18, ResNet 34, and ResNet 50. And next, let's talk about our method. This page shows our architecture. The architecture is mainly divided in 2 parts: token information and object relation finder, ORF. First, let's talk about token information. We hope the model to learn a relationship from the feature and players and ball. So the token information is important for the experience result. In our experience, the input information includes object coordinate, bounding box size, object class, and up to 17 join points. We found that providing the model with different feature information can improve the accuracy of judging ball handler. We add a join point of the skeleton because we observe that the player needs to rely on their hands to dribble or hold the ball. And the ball is usually located nearby the player's body during this action. Therefore, we think that adding joint point of the skeleton may increase the richness of the picture. Since transformers create a great success in natural language processing, we think we can use self-attention as a method to analyze the relation between object features in different tokens. First, the input token needs to undergo embedding block for dimension transform. After that, the ORF consists of 12 layers, each composed of 2 residual networks. The first layer consists of layer normalization and multi-head attention, and the second layer needs the layer normalization and the feed-forward network. And let's talk about multi-head attention. It plays an important role in this architecture. The input information will transform into 3 parameters, Q, K, V, then based on the value of n set for the number of heads, it's split into n set of Q, K, V. that self-attention to analyze the feature relation of each input token in multi-dimensional. About our self-made training dataset is include 2,892 features, and the label includes friend ID, tracking ID, bounding box position, width and height object class, and ball handler. And next, we'll show the experience result. All experience results shows on this table. We start with transitional algorithm, IOU, and Euclidean distance as our baseline. And we aim to improve the accuracy with deep learning method. So we use ResNet image compression to 3 different depths: ResNet 18, ResNet 34, ResNet 50. But the results were not very satisfactory. So we suspect that this is due to the small size of the data set or the frequent player overlap, which mislead the classification of ball handler in the image. However, using our proposed method, adding different feature information like bounding box location, object class, skeleton joint, let the model learn the relation between the player and the ball. Finally, we train the network on a small data set and achieve 91.16 accuracy rate, surpassing the baseline and ResNet method. And let's take a look at the demo video. This video shows the result of IOU method. The red bounding box shows who is holding the ball now. And we can see when the player overlapping, judging the ball handler will make a mistake. And this video shows the result of our method by using bounding box location, object class, and hand join as feature. We can see when player overlapping, our method is still able to judge the ball handler in most of the time. Finally is the conclusion. Based on a small amount of data set, our architecture has trained a ball handler accuracy rate 91.16%, surpassing the traditional algorithm 83.91%. And it's even better than CNN image calculation based on ResNet, 77.85% accuracy. In the end, the experience shows confirm that the object data analysis with transformer-based object relation finder can effectively solve most of the misjudgment of ball handler caused by overlapping players, thereby improve the ball handler judgment accuracy. And this page shows all my reference. This is end my presentation. Thank you for your attention and have a nice day.
Okay, thank you. Can we have a question from the floor?
And if you change the scene today, can your model still be used?
I think it's yes, because our method is to learn the player and the ball relation by coordinate information. So if your camera angle don't change too much, I think it will work in different scenes.
Okay, thank you.
Can you compare again the results you had with using a convolutional network instead of a transformer? You had much less accuracy with a convolutional block instead of a transformer.
why would you use a transformer instead of, for example, a convolutional approach?
Because we don't have a large amount of data set to train in the CNN method. So we think we use transformer to find, we use the self-attention to find the relationship between the player and the ball and give them the different feature on the players or the ball to find their relation.
So with little data, it's better to use transformer?
Yes, we use the, yes.
Thank you.
Do we have any other questions?
Okay, and thank you for your representation. And in your present, you talk about your data of basketball. So how much time does it take to create this basketball data set?
About 1 week. And this data set not only can use on this research, because I also mark the tracking ID and bounding box location. So this data set can use on object tracking and object detection in the future research.
Thank you. So I think that it's about time for us to welcome the last presenter. Who will be the last one? Wang Yushao.王玉少同学，你有来吗？Okay, so I think we can end of today's seminar. And then thank you for today. See you next week. Bye bye.
怎么办？要回去吗？我在想要不要买校门口。好啊。然后买回去吃一吃再过来啊，不然怎么办？在这里撑这么久。
think he's going to fail this class.
You think?
Because it's took 60% of the score.
So if you fail this kind of class, you have to do it again next year.
Maybe that's his plan.